Greetings and welcome to problem set number 6 of Chemistry 222, where we're going to look at both Chapter 17 and Chapter 20. They go kind of well together, so that's why we're doing them at the same time. I'm glad to have you here. Like the other problem sets before, make sure you have a periodic table in front of you. mhchem.org/per-tab is the one I recommend, so try to have that in front of you as you go through this problem set. Like on the other problem sets, make sure that you self-correct every problem. The problems you get right, put some kind of mark next to it so that I know that you know that it's right. Put one of those self-correct symbols or something comparable, doesn't really matter. On the other hand, you can miss problems, it's totally fine, but I do want you to self-correct the problems you miss as well. So cross out the old answer, maybe put in the correct answer, maybe make some notes as to how you do better the next time. Should be pretty chill. Problem sets turned in without any self-correct marks will not get full credit. Problem sets turned in with self-correct marks, even if you get every problem wrong, will get full credit. So make sure you put something next to each problem to get full credit. If you have questions on the material, I encourage you to talk to me. You can also talk to the Avid/LSC Center located above the library on the main MHCC campus. Their website is mhcc.edu/avid. They have free tutoring in chemistry for you as a Mount Hood Community College student. They're really cool people. I encourage you to check them out. Okay, without further ado, let's get into this problem set and see what these chapters have to offer. Give the equation for the relative rates of disappearance of reactants and formation of products for the following reaction. And then it says N2 plus 3H2 going to 2NH3. Then it says if delta H2 over delta T equals negative 4.5 times 10 to the minus 4 molar per minute, what is delta NH3 over delta T? Okay, this first problem, it's not hard, but it's really weird. And so of all the questions in problem set 6, this one is a little bit strange. But what it has to do is the way that scientists, and chemists specifically, talk about rate when it comes to a chemical reaction. And if it was a car and we wanted to know how fast it was going, all right, we would use miles per hour or kilometers per hour if you're in anywhere but the United States, basically. That's how we talk about rates or speeds when it comes to cars. But in chemistry, we have to think of a way to think about how fast reactions are too. This whole chapter is about time, okay? But the problem is that reactants, their concentrations are always going down, and products concentrations are always increasing. As the reaction proceeds, the reactants will be used up as they make the products. So products will be appearing, reactants will be disappearing. So when you want to talk about the speed of a reaction, it's usually in molar per minute or molar per second or molar per hour, whatever, some kind of moles per liter per minute. Now, sometimes it's like moles per minute, sometimes even grams per minute, although that's rare. It's some kind of amount of reactant or product for that matter being used up per unit time. So when you see molar per minute or molar per second, those are like speeds. And again, the analogy with a car would be miles per hour, all right? But of course, it's not distance over time. This is chemicals used up per unit time. But it doesn't really have to be chemicals used up. It can also be the products that are appearing per unit time, all right? And that's where it gets a little strange. So scientists have developed a way to describe the speed of a reaction regardless if it's a reactant or a product. But there are two things you must do. Number one, if it's a reactant, so for example here, like hydrogen, H2, that's a reactant, okay? If it's a reactant, you put a negative sign in front of it, all right? So all of the reactants over unit time are going to have a negative sign in front of it. Because the delta H2, the change in the reactant, final reactant minus initial reactant, it's always going to be negative because, again, reactants are being used up. So in order to make a negative number positive, scientists put a negative number in front of those speeds. So the first rule is that if it's a reactant, put a negative sign in front of it, all right? For a product, like over here with NH3, a product over time, you wouldn't put a negative sign in front of it. And you'll see how this will play out here in a second. The second thing you must do is in front of the speed, which will be strange looking, you always want to go 1 over the stoichiometry, okay? So for example, there with H2 in problem A, there's a 3H2. You would go 1 over 3, 1/3, in front of the way we're going to talk about the H2 speed. For the ammonia, and again, this is a different rule than the first one. For the ammonia, there's a 2 in front of it. We would put 1 over 2 in front of it, or 1/2. So again, those two rules, if it's a reactant, put a negative in front of it, but products leave alone. And rule number 2, you always go 1 over the stoichiometry. The speeds of these reactions will literally look like this delta H2 over delta T. It's going to be the change in the reactant or product divided by the change of time. So in a little bit, there's going to be 3 speeds here to talk about the relative rates. We're going to have a speed for N2, a speed for H2, and a speed for NH3. The N2 and the H2 speeds will have a negative in front of them because they're reactants. But the NH3, I won't put a negative in front of it because it's a product, it's positive. And the other thing we're going to do is we're going to go 1 over the stoichiometry. So for N2, it's just 1 over 1. We won't have anything there. But for H2, there will be a 1/3 in front of it, and for NH3, 1/2 in front of it. So again, remembering reactants are negative, products we leave alone, 1 over the stoichiometry. These are the quote-unquote relative rates of disappearance or formations of products. Now, let's look at the form here. All of these are delta, reactant or product, divided by delta T. Notice how the N2 and the H2 both have a negative sign in front of it, but the NH3, there's no negative sign, it's positive, all right? So again, products, we just leave alone, but reactants, you do put the negative sign in front. And the other thing, all of these have 1 over the stoichiometry. So 1 over 3 because of the 3H2, 1 over 2 because of the 1 over 2. But in front of N2, we just put 1 over 1 or left it invisible. Now, why this is cool is because all of these expressions here, they all refer to ways to talk about the rate of the reaction, the speed of the reaction. So unlike a car where you can only look at distance traveled per unit time, in chemistry, we can talk about the speed of a reaction from either a reactant or a product's perspective. So in some labs, maybe it's easier to watch the H2 being used up per unit time. No problem. Then you would use this version right here to talk about the rate. On the other hand, if you're in a different lab, maybe they have the equipment set up so that it's easier to talk about this one here per unit time. Cool, the ammonia appearing versus time. That's totally fine. Realize that an H2 would be disappearing, the NH3 would be appearing, but as long as those two are equal, you're good to go. So this is real powerful for chemists. Now, if everything I just said was gobbledygook, just remember the 2 important things to think about when you're writing a rate is that A, reactants get that negative sign in front of them, products you just leave alone, and B, you go 1 over the stoichiometry. If you can do those 2 things for me, honestly, you're good to go. Answer B, or question B, excuse me. It says the delta H2 over delta T is minus 4.5 times 10 to the minus 4 molar per minute. This number right here, minus 4.5 times 10 to the minus 4, that is literally the part that goes in these parentheses right there. That's what they call a relative rate. It's a rate based on just hydrogen. It's not the overall rate of a reaction because H2 is disappearing a lot faster than N2 is. That's what the 1/3 is out there for. And also remember that reactant concentrations are constantly going down. That's why it's negative 4.5, all right? While the products, the NH3, are constantly appearing. So those numbers will always be positive. So in part B, we literally want to translate the relative disappearance of H2 into a relative appearance of NH3 over T. So essentially what we want to do is we want to think about this part here in square brackets as just an X to solve for. X is the delta NH3 over delta T. And to do that, we have to multiply both sides by 2. Because we want to get, I'll put a 2 right there. We want to have the 2's cancel out, so we have just X on one side. So on the other side, you'd have negative 2/3 times parentheses, negative 4.5 times 10 to the minus 4. You plug all that stuff in. You end up getting 3.0 times 10 to the minus 4 moles per liter, okay? So let's look at this a little bit more detail. Again, this part right here, the delta NH3 over delta T, is like the X to solve for, all right? And in order to solve for it, we had negative 1/3, and that's where that 3 comes from, delta H2 over delta T. We had to multiply both sides by 2, all right, in order to get the X part by itself. And notice here how it really comes down to a factor of stoichiometry, because there are 3 moles of H2 used up for every 2 moles of NH3 that appear. That's where another use of these 1 over stoichiometries. It's very wild how this stuff works out. And because the delta NH3, because the delta H2 over delta T was a negative 4.5 times 10 to the minus 4, and there is a second delta in front, which I'm going to circle right there, you can see how the negatives cancel out. You're going to end up with a positive number. The positive number is good because NH3, a product, is appearing, so those numbers should be positive anyway. Good to go. I find that on these problems, a lot of times at first it's like, what the blank are you talking about, Russell? But if you break it down and think about, well, we just want to solve for X right there, then we multiply both sides by 2, the negatives cancel out, etc. Then it becomes a little bit easier. But you're turning the speed of the H2 disappearing, which is what the negative 4.5 times 10 to the minus 4 number is. You're turning that speed into the speed of ammonia appearing, which is 3.0 times 10 to the minus 4. So you can see the H2 is being used up a little more than the NH3 is appearing, like 4.5 is bigger than 3.0. Whoa. Welcome to the world of kinetics. Now, all of the problems we're going to see from here on in, they're going to talk about a rate, all right? And sometimes the rates will be given to us or sometimes we can find it. But this part right here, these are all the different ways that you can describe the rate for a reaction. You can think about it from the reactant's perspective or the product's perspective, but make sure, like I said again, put a negative in front of the reactants, 1 over the stoichiometries for everything. You are good to go. Nitrosyl bromide, NOBr, is formed from NO and Br2. Experiment shows that this reaction is second order in NO and first order in bromine. The equation is given right there. Then it says write the rate law equation for this reaction. Then it says how does the initial reaction change if the concentration of bromine goes from 0.0022 to 0.0066. And then it says, and C, what's the change in the initial rate of the concentration of NO is changed from 0.0024 to 0.0012. All right, no problem. A rate law is something that chemists can use to describe like why a reaction is fast or slow. And if you know things about the rate law, there's a lot of power you can have over a chemical reaction. So in this problem, it says that the reaction is second order in NO and first order in bromine. So when you want to write a rate law, you always start off with the rate. And rate is what we talked about in question 1, and all of those things from question 1 you could put in for rate. Rate equals K times the reactants, and the reactants will be raised to a power, all right? And in this problem, they're giving us those powers. They call them orders. It says that NO is second order, bromine is first order. So for this problem, the rate law it would be rate equals K times NO to the second power, or squared. That's what it means to be second order. And bromine is first order, so it would have like an invisible superscript 1 right there. So we usually just don't use the ones when they're there. This is an example of a rate law. Now the rate, the left-hand side of the equation, can equal all of those things we talked about in question 1. So, 1 over the stoichiometries, negatives in front of reactants versus products, any of those can be plugged into this rate part, the left-hand side of the equation. And that equals then always a rate constant K times the orders, times the reactants and their orders, and you're good to go. This is what it means to have a rate law. Now, why chemists get excited by this is you're going to see in the next 2 questions how changing the concentrations of these reactants can have a pretty big change on how fast a reaction goes. So let's say that we have all of this stuff done, and on B, we're changing the bromine concentration from 0.0022 to 0.0066. Well, 0.0066 divided by 0.0022, you can probably see that's a factor of 3. So we're going from the 2 to the 6 value. That's increasing the concentration by 3 times. If you start changing the concentration, you will change the rate. And we know that because bromine is one of the parts of the rate law. And essentially what we're doing here is we're increasing the bromine, the part in square brackets, by 3. And bromine is a first order reactant. It's an invisible 1 right there. 3 to the first power, which is what the 1 means, would be 3. We would predict that the rate goes up by 3 times. So your normal, like say 20 miles per hour car would all of a sudden be 3 times faster, 60 miles per hour, something like that. That's what would happen if we increase the bromine concentration by this factor of 3. All right. This is the process that happens when you have a first order reactant like bromine. Anything to the first power, if you change the concentration, you're going to change that speed quite a bit too. In this case, it will be 3 times faster than it was before. So to figure this out, you look at the change in the reactant concentration, and this was a factor change of 3. You raise it to the power, so bromine is a first power, so 3 to the first. The rate's going to go up by 3. Now we're going to do something similar on C, but notice here how this is first of all NO, not Br2, and we're taking it from 0.0024 down to 0.0012. So 0.0012, which is the new concentration, divided by 0.0024, that's a factor of 1/2 or 0.5. We are lowering the concentration of the NO. Okay, so just like in the last problem we had a factor of 3, in this problem we have a factor of 1/2. Like the last problem though, what we're going to do to see the effect on the speed or rate is we're going to take that 1/2 and raise it to the power. Bromine was a first order reactant, so 3 to the first ended up giving us a rate change of 3. But in this problem, NO is a second order reactant. So we need to take that 1/2 and square it, raise it to the second power. That's going to be the effect on the speed. Well, if you haven't done fractions raised to the power for a while, I can't understand. No, seriously, I don't do this either that much. 1 squared is 1. And on the bottom, my pen's kind of freaking out here. 1 squared is 1. 2 squared is 4. So what this 1/4 says, the speed of the reaction is going to go down to 1/4 of what it was. So imagine in this case that you have a 20 miles per hour car and you change the concentration, you lower it to half of what it was. Your speed doesn't go down by 1/2, it goes down to 1/4. So it goes from 20 miles per hour to like 5 miles per hour. Whoa, okay? Anyway, this is the chemist's version of whoa in a chemical reaction. Anyway, we took that factor, that 1/2 factor, and you just raise it to the second order power, raise it, square it, okay? And that's where this 1/4 part comes from. So first order reactants, all right, will definitely have a big difference. Like we tripled the concentration, rate goes up by 3. But second order reactants, man, you change their concentrations just a little bit. And because you square the difference like we're doing here, the rate effect is pretty big. If we would have tripled the NO concentration in C instead of taking 1/2 of it, then we would have went 3 squared. It would have increased by a factor of 9. So the rate law helps the chemist to see why rates are fast or slow. We're seeing the factors that make a reaction go quicker or slow it down quite a bit. Here's the reaction 2NO plus 2H2 going to N2 and 2 water. And it's being studied at 904 degrees Celsius. And the table on the right there, that's the data they collected. So this problem has several parts. First, it says determine the order of the reaction for each reactant. B, write the rate law equation for this reaction. C, calculate the rate constant K for the reaction. And then D, find the rate of appearance of N2 at the instant where NO equals 0.350 and H2 equals 0.205. All right, so on this page right here, we're going to tackle A and B, and on the next page, we'll look at the other one. So let's talk about, first of all, A, how to find the order of the reaction. Now, first of all, I think it's important to realize if you're going to write a rate law, it's almost always rate equals K, and then you put the reactant. So in this case, it would be NO, but we don't know what the order is. So I'm just going to put a generic X up there. And the other reactant here would be H2, and I'm just going to put a generic Y right there. So in this question A, we want to find the value of X and Y. And in Chem 222 and Chem 223, the values of X and Y, the orders of reaction, are only going to be 0, 1, and 2. All right, so there's not that many choices, but those are the things we're looking for. Outside of Chem 222 and 223, you might see fractional bond orders, and that's a whole nother ball game. But for right now in our class, just 0s, 1s, and 2, which are by far most common. That's what we want to do in A. And what I would do if I was a scientist trying to find X and Y is I would literally take different concentrations of the reactants and products. And I'm going to name these trial 1, trial 2, trial 3, and trial 4. So notice that this is the same reaction, NO and H2 making stuff. And on the far right, we have the rate, all right? That's the rate part of the rate law. And we're trying to find out how changing NO affects the reaction. And so what you can do is look for a set of experiments where one reactant changes, but the other one doesn't. And as an example of this, notice that in number 2 and number 1, the NO, if you go from 2 to 1, is doubled. 0.210 times 2 is 0.420. But the H2 stays the same. So any effect in the rate, which is these two numbers here, any effect on the rate is going to be the result of NO. It's going to be observed in the order of the reaction because H2 is staying the same. Nothing's going to happen because H2 is stay the same, so the rate change has nothing to do with the H2. So in a problem like this, what I would do is I would go for example, 0.420 divided by 0.210, and you can see that's a factor of 2. But I would also do the same thing on the rate side. So I would take 0.136 divided by 0.0339, and in your calculator, which I would have to do because I can't think about this kind of stuff, this factor, it's about 4. So look at the 2 and look at the 4, all right? We're changing the reactant NO to twice as what it was, all right? We're going from 0.210 to 0.40. And remember, this NO is going to be affected by a factor X. That's the order of reaction. And 2 to the X is going to equal a change in the rate of 4. So notice what I did there. I'm looking at just NO because H2 is staying the same. K is also staying the same. So K only changes if you change the temperature, and we're not doing that. So it's really like NO, the change of NO to the X power equals the change of the rate. So 2 to the X equals 4. Now remember in Chem 222 and 223, X will only be 0, 1, and 2. So if X was 0, 2 to the 0 power would be just 1. So X is not 0. Let's say that X was 1. 2 to the first power would be 2. So X is not 1 either, because 2 to the 1, 2. 2 is not 4. That's not going to happen. On the other hand, if X is 2, 2 squared equals 4. It looks like NO is a second order reactant, all right? And we know that because we changed NO, we doubled NO, the rate went up by 4 times, 2 to the X equals 4, X here is gonna be 2. Now, for H2, we wanna also find a set of conditions where the NO now is not changing, but the H2 is. So I would use number 3 and number 2, because notice that NO is 0.210 on both of those, but H2 goes from 0.122 to 0.244. H2, 0.244 divided by 0.122, that's a factor change of 2. And if you do the same thing by looking at the rates over there, 0.0678 divided by 0.0339, that's a factor of 2 as well. So for H2, we have a change in the concentration of H2 to the X equals 2. That little x or y, as I wrote earlier, either way, can only be 0, 1, and 2. The only time where 2 to the x equals 2 is if the order equals 1. So this is one way that you can go through and find these orders of reaction. You want to have a series of data, and you're going to change one reactant concentration while leaving the other one the same. And if you do that, you can isolate these orders. So this is a lot of words, but it basically tries to show here what I just did. In the first 2 sets of data, so number 1 and number 2, H2 is constant, 0.122 in both. NO is halved. Okay, well, they're looking at, I forgot, that's right. So 0.420 going to 0.210 would be like a factor of 1/2. And the rate decreases by a factor of 4. So what that means is 0.0339 divided by 0.136. So 1/2 to the x equals 1/4. X has to be second order. Now notice that what I did in the description earlier is I used the bigger number divided by the smaller number. I personally think better that way, so you don't have to go, first on the bottom, second on the top. I would always try and have the bigger one on top. Then you get 2 to the x equals 4, which is easier to me, but anyway, it's up to you. But there's multiple ways to find these orders, as you can see. Now this last sentence there, it says, looking at the second and third data sets, NO is constant and H2 doubles. So as the rate doubles, 0.0339 to 0.0678, and the H2 is doubled, 0.122 to 0.244, then you do have the 2 to the x equals 2. Only way x is going to work is if x is 1. So by hook or by crook, this is a great way. In the kinetics lab for Chem 222, we're also going to look at a different way with logarithms. If you don't like this, looking at reaction concentrations, finding order, which maybe is too touchy-feely, I dig it. You can also use logarithms to find the value of x, and I'll leave that for the lab and stuff as a way. But if you can do this, this is obviously a little less work, and it becomes pretty easy after a while. If you have a second order NO and a first order H2, which is what question A was all about, we can then write the rate law. The rate law equals K times NO to the second power times H2 to the invisible, if you will, first power. And why I want to talk about this real fast is that if you look up here in the original stoichiometry of the reaction, this part right here, here, the 2 of NO and the NO second power fortuitously are the same. Like NO is second order and there's a 2 in front of the H2. But notice the H2 also has a 2 in front of it, but we found here that H2 was a first order reactant. So the stoichiometries, the 2 and 2 in this reaction, are not always going to be the same as the orders of the reaction. Here we have a 2 for NO, but only a 1 for H2. And we'll talk about why this is the case later on, but for right now, just realize the stoichiometries, you shouldn't assume by default those are equal to the rate orders. The orders might be completely different. You must have an experiment to really tell for sure. In the last part of the problem, we saw that rate equals K times NO squared times H2. So now see there, it says calculate the rate constant for the reaction. The rate constant is that little K right there. And for this problem, you can literally use any set of data you want to. So let's say that I was going to use number 1. All right, well, rate 0.136, that would be that number. I don't know K, that's what we want to solve for, but the NO concentration would be 0.420, and I would square that number because it's second order. And the H2 concentration, 0.122, that would be raised to the first power just by itself. So notice that the only thing here we don't know is K, but you don't have to use experiment number 1. You can use experiment number 2, experiment number 3, experiment number 4. In the best world, you would calculate 4 values of K and then find the average in parts per thousand. If you don't feel that adventurous right now, I completely understand, i.e. boring. I'm sorry, I mean really interesting as a scientist, but yeah, at least find one of them. That's kind of the goal of this problem, but you see how this kind of stuff works. So in this problem, I did use number 1, and again, you can use anything you want. The rate for number 1, 0.136. Here's the NO concentration squared. There's the H2 concentration. The rate came out to be 6.32. I did calculate K for the other trials. They're actually, all the other ones are 6.30, so the average 6.31, etc., etc. So hopefully you get the idea. If your number's somewhere in there, that's awesome. Now, I included the rate value K units. They're very weird. It's basically 1 over molar squared, 1 over seconds, all right, per second, something like that. People don't usually report the values of K, the units of K, because they're really, really weird, okay? But if you're curious, this is what it would be for this problem. I will not be asking you for the units and stuff on these because they are kind of unusual, but you can calculate them. Every K is a little bit different, you're going to see as we go through this chapter. Now finally, once you have the rate K, then you can find the speed of the reaction for any set of concentration values. So in part D, it says find the rate, the speed. All right, it says when the NO is 0.350 and the H2 is 0.205. Well, we've got our K value now, 6.32. That's K. NO squared, so NO is 0.350, and we're going to square it, times H2, 0.205 to the first power, speed 0.159 molar per second. All right, so this is the way to set the speed for a reaction if you have K, and that's really cool. Finding K is kind of a big thing in the kinetics world. This problem is a lot like the kinetics part 1 lab that we're going to do. We're also going to set a set of conditions, find the rate orders for the reactants, and then finally in that problem, in that lab, we're going to solve for the rate constant K. And in that one, you will take an average of the K's, parts per thousand, blah, blah, blah. All stuff you can do. The decomposition of N2O5 and carbon tetrachloride is a first-order reaction. If 2.56 milligrams of M2O5 is present initially and 2.50 milligrams is present after 4.26 minutes at 55 degrees Celsius, what's the value of the rate constant K? Okay, this question, which is going to be very similar for the next several questions, involves what's called the integrated first-order rate law. And that's a really cool equation that works works anytime you have first order reactions. Now, most reactions in the real world are first order. Everything that's biology related is first order. Everything that's related to nuclear chemistry is going to be first order. And honestly, most regular chemistry reactions are first order too. So if you have one of these first order, this is a really cool equation to use. Natural log R over R0 equals minus KT is the form of the integrated first order rate law. And as we talked about in lecture, R0 there is how much you start with, and R on the top is how much you have left at time t, and K is the rate constant. Right now, R and R0 are written in square brackets, which makes it look like they're molarities. But in reality, R and R0, that's a ratio. So you can use molarity over molarity, absolutely. But because they're the same flask, the liters would be the same. So that would be also moles over moles 0. And because moles can be converted into grams, it could be mass in grams over mass in grams 0. And of course, if you can do mass in grams, it can also be milligrams. So there's lots of different things that you can plug into that R over R0 ratio, all right? As long as they're the same kind of unit, it works out really well, and we're going to see some utility for that. ln is the natural log. It's not the base 10 log, which is listed as log. So make sure that when you're doing these problems, you use the natural log, the ln button. Okay, that's really, really important. Log will give you totally different answers. And then on the other side, you have K and T. So T is time. And in chemistry, time is always a positive number. There's no negative times. Darn it. All right. Wish you could go back in time sometimes. I understand. But anyway, in chemistry, time is always positive. Just like mass, grams is always positive in chemistry. Okay. So if time is positive, K is related to time as well. K is the rate constant. And both rate constant K and time t will always be positive numbers. There's a negative sign in front because R over R0 is going to be a number less than 1, which creates negative logs. That's nothing we need to worry about. But you need to just remember that K and T will always be positive numbers. And another thing, K and T are going to have the same kind of units. Now, time in this problem is going to be minutes, all right? That's the time elapsed. K for this problem is going to have units of inverse time, which means 1 over time. And if time is in minutes, then K is going to be inverse minutes, or 1 over minutes. So if time would be hours, K would be inverse hours. If time is milliseconds, K would be inverse milliseconds. Both K and T are positive. Their units are the same kind of units, but of course K is inverse time. So knowing all that, a lot of these problems are just good old plug and chug. In this problem, we're going to have the N2O5 divided by the N2O5 we started with equals minus KT. So milligrams, we started with 2.56 milligrams, and after 4.26 minutes, we had 2.50 milligrams left. So you can see there the initial was 2.56 on the bottom, 2.50 is what's left on top, 4.26 minutes was the time elapsed. K is going to be the rate constant K, and again, K and T, always positive numbers. So if you've done the problem right, if you use natural log, you should get a K 0.00557 inverse minutes. Now, you can translate these things into seconds as well. And on this problem, I've had people go 4.26 minutes times 60 seconds per minute. So you can translate the minutes into seconds, and that's totally fine if you did that. I got a 9.28 times 10 to the minus 5 inverse seconds if you use seconds for time, and that's totally fine. It doesn't specify what kind of rate constants you have. So anyway, first order integrated rate law, super important. The next several problems, we're going to be focusing on this equation and the things you can do with it quite a bit. Gold 198 is used in the diagnosis of liver problems. The half-life of gold 198 is 2.69 days. If you begin with 2.8 micrograms, that's the micro symbol, 2.8 micrograms of the gold isotope, what mass remains after 10.8 days? Okay, so this is a problem with a radioactive isotope, and anything with a radioactive isotope, as well as anything in biology basically, will be a first-order reaction. So in this problem, what I would do is I would start with natural log R over R0 equals minus KT. And if you dig through this problem, we started R0 with 2.8 micrograms. We want to know how much is left, which would be R, and R would be some value of micrograms less than 2.8. We want to know how much is left after 10.8 days. So 10.8 days is T. But we run into a problem because we don't have K. All right, we don't have a rate constant K. We're looking for R, but we need K in order to find it. Like we have one equation with two unknowns, and that's a bad thing. So along with the first order integrated rate law, I highly recommend that you also commit this to memory or whatever you need to do. Half-life 0.693 divided by K. This equation goes really well with the first order integrated rate law, and this is something we talked about in lecture. But we have here in this problem, we have the half-life of 2.69 days. So we can put that in for T1 half, which is the half-life. 0.693 divided by half-life will equal K. We'll solve for that. And then finally, we can put it back in the first order integrated rate law to see how much R is left over after this 10.8 days. So this is the first time we've seen half-life. Half-life is the time it takes for half of the sample to decompose. So in this problem, 2.8 micrograms, the time elapsed for it to go down to 1.4 micrograms, half that number, 2.69 days. But in our world of Chem 222, half-life equals 0.693 divided by K is going to be much more useful because we can put that into the value for K and be good to go. There's a couple different ways you can actually do this problem, all right? The cheesy way, the Chem 104 way, as I called it in lecture, is to literally see if you have an integral number of half-lives. And what I mean by that, in this problem, you would take the time elapsed, 10.8, divide it by the half-life, 2.69, and it does come out to be 4 half-lives, all right? So one way you could do this is you could take the initial amount, 2.8 micrograms, and multiply it by 1/2 raised to the number of half-lives, 0.18. Another way to think about that is if you started with 2.8 micrograms, you would go down to 1.4 micrograms after 1 half-life, then 0.7 micrograms after 2, 0.35 micrograms after 3, and half of that is pretty close to 0.18. 0.175 raised up would be 0.18. This is honestly totally fine to do it that way. All right. The way that I prefer you to think about it is using the first order integrated rate law. Natural log R over R0 equals minus KT, but because we don't know K, 0.693 divided by the half-life is also equal to K. So I didn't even solve for the rate constant here. I just plugged it in like that, multiplied it by 10.8. Slightly different answer, 0.17 micrograms versus 0.18 micrograms. The doubtful digit, all right, is a player in all of this, all right? And so in this problem, you should be careful, but it's not a big deal. In any scientific thing, the last digit listed is that doubtful digit where there's some plus or minus. And you can see that the method you take here will determine the answer. I would give you credit, i.e. mark correct, for either one of these answers, so don't worry, okay? But do realize that if your friend does it in the second way and you did it the first way, you might see slightly different values. As long as that last digit is plus or minus 1 or so, you're good to go. Science, chemistry especially, very experiment-based, and this is the kind of stuff you run into when it comes to this kind of material. Ammonia, NH3, decomposes when heated according to the equation shown on the right. Data in the table was given and collected at a high temperature. Then it says plot ammonia's concentration versus time, natural log of concentration versus time, and 1 over concentration versus time. What is the order with respect to NH3? Find the rate constant for the reaction from the appropriate slope. Okay, we're entering an area now where we're not sure if this reaction is 0 order, 1st order, or 2nd order. And the goal of plotting all of those different ways of this data is to test, is it 0 order, is it 1st order, is it 2nd order? Okay, so we're going to use that table a lot. Now, if you have used a program like Microsoft Excel or Numbers on the Macintosh, or Sheets, I believe it is, and Google, any of these kind of things, these problems are a lot easier, all right? Because you're going to be graphing a lot of things, and knowing how to manipulate tables and stuff can be really, really handy. But let's first talk about what's going on here. So first, you want to plot these different values. So the first one is easy. We have the NH3 concentration values. We'll plot those versus time. That's going to be the NH3 versus time. Now, natural log NH3 versus time means you have to take natural log of the NH3 values. So natural log 8.00 times 10 to the minus 7th equals some number, all right? Those are the numbers you're going to plot versus time for the 1st order test. 1 over the concentration means 1 over 8.00 times 10 to the minus 7th, and that will be a number. And those sets of numbers versus time are what you want to plot on the 2nd order. Now, you're going to end up with 3 graphs, and the way to figure out what the order is you apply a linear regression to each one of them. And a linear regression, you'll look for the best fit, i.e. the best correlation coefficient R. So the best R will lead you to the order, and from the order, you'll be able to find the rate constant K. So in this next picture here, I'm going to show you the results here of what I did. So there's the raw values. This is something I did on Excel, and I'd like you to focus up here in the upper left corner first. The first column is time. I then put in the values of C, 8.00 E minus 7. Notice the E notation. On Excel and Apple Numbers and Sheets, they like E, so don't put in 8.00 X to x10 caret minus 7. Usually Excel and those programs aren't smart enough to figure that out. So if you want to plot 8.00 times 10 to the minus 7th, go 8.00 E minus 7. And it can be in this form, either big E or little e, but that's how you get those numbers in. There's a command in these values of Excel, or programs like Excel and Numbers. You go equals and then ln parentheses, and you click on the cell. So like click on the 8.00 e to minus 7. And then there's also a fill down command in these programs. This is really handy. So it makes short order of these kind of problems. It's pretty cool. The far right corner is literally 1 over 8.00 times 10 to the minus 7th. The really small numbers become really big. Anyway, then after I had the values, and you can do it manually, but I'm trying to give you hints how to do it, let the computer do the hard work for you. There's basically 3 graphs: a 0 order in the upper right, a 1st order in the lower right, and a 2nd order kind of middle part center, all right? And so you can see they're the different values. So in the 0 order test in the upper right, concentration versus time. Middle one here, it's 1 over concentration versus time. And then the last one, natural log of concentration versus time. If you look at the values, the little dots, and you compare them to the linear regression, which is the dark line in the middle, all right? The 0 order test has dots both below the line and above the line. And that probably means that it's not the best data for this linear regression, all right? But if you look at the other two, it's harder to tell, all right? They both look pretty good. But the linear regression will actually tell you what the best fit is, and that's where these little R values come in. So you can see that for 0 test, R was negative 0.9913. Correlation coefficients are negative when the slope is negative. Correlation coefficients are positive when the slope is positive, like on the second order. So that's what's going on there. Anyway, the R value for zero order minus 0.9913, and that's not a bad fit, all right? The closer it is to -1 if the slope is negative, or +1 if the slope is positive, is good. And if you look down here in the bottom right, the first order was even better, minus 0.9977. So if you were comparing zero and first order, you'd say, well, this reaction looks like it's first order because you have a better R value, a better correlation coefficient. So it's definitely not zero order. It could be first order, but we also need to see if it's second order. And remember, most reactions are first order, but lo and behold, in this particular example, the R value is exactly equal to 1. That's perfect data. Made up, excuse me. Anyway, sorry, I didn't mean to make that slight comment. R of 1, if it's positive slope, is the very best correlation possible. If you had an R which was -1, that would be the best for a negative slope. But in this case, R of +1, this is definitely a second order graph, okay? So notice how we use the R values to tell what the best order of the reaction is. And this one is definitely second order because it has the best fit. The slope is related to the rate constant K. And like we talked about earlier, rate constant K's are always positive. So if your slope is positive, then the slope literally equals K. If the slope is negative, then K equals the negative of the slope, i.e. make the K positive. So in this case, because it's second order and the slope, which was next to the Y value there, next to the X value, the slope is positive. That means the slope equals K. So to 3 sig figs, which is what the concentrations are, the slope here would be 9,220. I raised 9224.4 to 3 sig figs because of the 3 sig figs in the concentration. Down here for first order, if this would have been the best fit, then we would have said the K value equals positive 0.00590, 3 sig figs, I guess. But anyway, notice how I made the rate constant positive. Rate constants are always positive, but for a first order test, the slope is negative. So slope equals negative K. K would be the opposite of slope. So what you're seeing here is if you're a scientist studying a reaction for the first time and you don't know what order it is. I mean, most of the time they're first, but are you really certain? And never say for certain when you're a scientist. So you should graph the data in these different ways. And in this particular set of data, we saw that 1 over concentration versus time had the best fit, the best R value. So this is a second order reaction. And the slope is related to the rate constant K. K always is positive, so in this case 9220 equals K. If you had a best fit for one of the other ones, then you take the opposite of the slope to find K, because again K must be positive. So in this problem, just to make sure everybody's clear, best fit is 1 over concentration versus time because of the K value. Reaction is second order. K equals 9220, which is the positive version of the slope. K is positive. Life is good. Answer the following questions based on the reaction coordinate diagram shown on the right. Notice that on the right, that picture there kind of looks like a person that's fallen down. I don't know, I have a weird sense of humor, but anyway, the important part for us here is not your instructor's impression of pictures, but notice that reactants are on the left and products are on the right, okay? So we're seeing here basically an energy diagram for how reactants go to products. And the first question says, is the reaction exothermic or endothermic? Well, exothermic reactions have negative delta H's, and that means that overall energy is released. But you can probably see here, products are at a higher energy than reactants. So if you go straight from reactants to products, you have to add some energy in. This reaction is not going to happen unless you add some energy. Adding energy to a reaction makes this reaction endothermic. Here's pictures that show reactants going to products, and you can see the top one is like what we have right here. It's an endothermic value because reactant energy is lower than product energy, and in that case you have to add some energy. You'd say that delta H was greater than 0 endothermic. We'll see a lot of examples with the lower graph, though, where reactants are at a higher energy than products. In those cases, going from reactants to products, you would get energy out. Your delta H would be negative. In those cases, you'd have an exothermic reaction. So one cool thing here is you can quickly see if a reaction is going to be endothermic or exothermic. Look at where reactants and products lie. Now, the second part says, does it occur in more than one step? And if so, how many? Each one of these humps in the graph is a step. And in a mechanism, which we'll start talking about here, we would say that this was a two-step mechanism because there's these two humps, all right? So yes, this reaction is going to occur in two steps. The graphs that I showed on the far right are like this one here on the far left. Those are single-step mechanisms. They only have one step. All right. Well, but you can have two steps like the one here. You can have three steps. There are ones that are even four steps sometimes. Lots of different things. But what you need to know is that the number of humps is how to tell how many steps there are. Single step mechanisms have different types of behavior than dual step mechanisms. And in the picture of number 9 at the top right there, this is a two-step mechanism. What is the rate law equation for each of the following elementary reactions? This question is introducing us to what the heck an elementary reaction is. And an elementary reaction is just a single step mechanism. So if we were going to draw a little reaction diagram like we did on the last question, all of these reactions, this would be like reactants going to products, all of them would have a single step. They would all be something like this. And again, this is reactants on the left, and we have products on the right. It would be single step. In the last example, we saw two humps. That's not a elementary reaction. That would actually be a multi-step mechanism. So elementary reactions literally mean single steps. And if you have an elementary reaction, then all of the reactants will appear in the rate law. So maybe it's easier to say. So first of all, elementary reactions are just single step reactions, and all reactants appear as they are in the rate law. So for A, rate would equal K times Cl times ICl to the first power. Now, in an earlier problem, I said, oh, don't necessarily think the stoichiometry is the same as the rate law. Well, what I should have said, I guess, now knowing this conversation is, if it's an elementary reaction, then the stoichiometry is the same as the orders in the rate law. These aren't that common, so it's why I feel okay about making my earlier statement, but just realize that, yeah, rate equals K times Cl times ICl. So the second one would be rate equals K times O times O3. I'm literally putting the reactants in their orders right there. And the last one, you could write rate equals K times NO2 times NO2, or rate equals K times NO2 squared. So in all of these reactions, they're single step, an elementary reaction. So in the first one, you'd have a Cl and an ICl bouncing into each other. In B, you'd have an O and an O3 bouncing into each other. And in C, you'd have two NO2s crashing into each other to make N2O4. This is kind of what first order and second order means. A second order means literally in a rate law that you've got two reactants coming together, two of the same kind of reactants coming together to make something happen. And we're going to see this as we go through. So this only applies if it's an elementary single step reaction, all right? And we're going to see there's lots and lots of examples where you don't have elementary single step reactions. But if you do, reactants literally will be the same as the orders in the rate law. The reaction of NO2 and CO is thought to occur in 2 steps, and you can see there's step 1 and step 2. Notice that step 1 says slow and step 2 says fast, and that'll be important for us. All right, first one, add the elementary steps to find the overall stoichiometric equation. Okay, so what we're looking at here, this is a mechanism, and a mechanism is how reactants go to products. A mechanism itself, though, will sometimes have some confusing pieces to it. We'll talk about that here in a little bit. So to find what's really happening chemically in this reaction, you just add up reactants and products for both of the steps. And if you had 3 steps, you could add up all 3. So what I mean by that is if you look at this reaction long enough, there's an NO3, which is a product right there, and there's an NO3 that's a reactant. So if we added step 1 and step 2 together, the NO3s are on both sides. They would cancel out. NO3 is not part of the overall reaction. And if you look also a little bit longer, you'll see that an NO2 out as a product can cancel one of the NO2s that's a reactant. So the pieces that are left over that don't cancel here are going to be NO2 plus CO, making NO plus CO2. And again, this is another way that I wrote right here to show you what it is. The parts that cancel out are not part of the stoichiometry. So up until this chapter, I would have just said nitrogen dioxide reacts with carbon monoxide to make nitrogen monoxide and carbon dioxide. I wouldn't have said anything about the pieces we canceled out, and we wouldn't have talked about the steps involved to make this happen. But again, to make NO2 and CO react, you have to go through this 2-step process, and that's really important. B, it says what's the molecularity of each step and which step is rate determining. Molecularity is a term, and there's basically 3 choices. You can be unimolecular, bimolecular, or termolecular. Unimolecular means that there's one reactant breaking down to multiple products. Bimolecular means 2 reactants are coming together to make products. And termolecular means 3 reactants are coming together to make products. Well, both step 1 and step 2 have 2 reactants. Step 1 has 2 NO2s. Step 2 has an NO3 and a CO. We would refer to both of those as bimolecular steps. And rate determining step, or RDS, is nothing more than the slow step. So for this problem, for part B, you would say that both step 1 and step 2 are bimolecular because you have 2 reactants coming together. Step 1 is the rate determining step, the RDS, and we're going to see that's pretty important here in a little bit. But again, just look for the slow step, which the scientists would have to tell you at this point to figure out what the RDS is. Now, C, for this mechanism to be consistent with kinetic data, what must be the experimental rate law equation? And this is really important. You can make a mechanism in a whole bunch of different ways to explain how NO2 and CO comes together to make NO and CO2. But if it's done right, if you make a good mechanism, then the slow step reactants should show up in your rate law. Now, to find a rate law, you have to do what we've done earlier in this problem set. You take the reactant concentrations and you vary them. You try and find the order for the reactants and then the rate constant K, stuff like that. The slow step reactants should be present in the rate law. So because step 1 is the slow step, and because NO2 appears not just once but twice, if this is a good mechanism, your rate law should equal K times NO2 squared, because in that slow step, 2 NO2s are coming together to make whatever they make. 2 NO2s means a second order reactant. It would think about the unimolecular or the elementary reaction problem we looked at earlier. Now, also, CO doesn't appear in the slow step. It's part of a fast step. So if this is is a good mechanism, then when we go to the lab and we vary concentrations, we should find that NO2 is a second order reactant, and we should also find out that CO is a zero order reactant. CO would have no effect on the speed of this reaction, and that's a pretty tall order. But if our mechanism is valid, then the rate law should correspond to the slow rate determining step of our mechanism. If you propose this two-step mechanism and you find that the rate law equals K times NO2 times CO, i.e. their first power, then you can throw your mechanism out. It doesn't mean anything. It's like science fiction, what you've made up. The rate law step should correspond to the slow step if it's a good mechanism. So in this problem, they really feel that two NO2s are smacking together to make the weird NO3 and NO. That's the slow step, and the slow step determines how fast the overall reaction goes. So again, I can't highlight this enough. The slow step reactants should be present in the rate law. And if there is a reactant that's not in the rate law, like CO in this case, that means it's a zero order reactant. It's not part of the slow step. Okay, one more thing. We crossed out NO3 when we combined the two steps to give the overall reaction, and we also crossed out an NO2. And both NO3 and NO2 have kind of special names. NO3 is referred to as an intermediate. An intermediate appears in a reaction and then is used up again in a subsequent step. So we would refer here as NO3 as an intermediate. NO2 is acting as a catalyst. A catalyst is used up in an early step and regenerated towards the end. I would say that this reaction has self-catalyzing NO2. It's self-catalyzing itself. It's making the reaction go. So an intermediate is appearing and disappearing in a mechanism. A catalyst is being used up and then being regenerated in a subsequent step. And both of those things you'll run into in mechanisms. Intermediates can be really helpful. If we propose this two-step mechanism and some scientist says, no, your data is ridiculous, it's not worth anything. If we could detect NO3, and they have like laser spectroscopy ways to do this kind of stuff, if we could detect NO3 just for even a little bit, that would be evidence that our mechanism is valid. And so sometimes intermediates can really help solidify the fact that our mechanism is valid and stuff. So in science, this can be kind of a cool thing. The data in the table shows the temperature dependence of the rate constant K for this reaction. And then it says plot these data to derive the activation energy and frequency factor. Okay, we just went through some problems where we looked at the different humps of a reaction. And each of the humps is a positive value. It's an energy barrier that reactants must go over in order to become products. And the hump's official name is activation energy, or energy of activation. And finding the energy of activation is a big part of chemistry. As the activation energy gets bigger, the time that a reaction takes to complete becomes greater too, because you have to have the right kind of energy, the right kind of geometry, stuff like that, so it becomes more complicated. So what chemists do to find the energy of activation, or activation energy, as well as the frequency factor, is they'll find the rate constants K over a given range of temperatures. So here you can see we've got a bunch of Kelvin temperatures and a bunch of rate constants K. This problem involves what's called the Arrhenius equation. And in the Arrhenius equation, you want to plot the natural log of the rate constant K versus 1 over the Kelvin temperature. So what we're going to do to the data up there is we're going to take the natural log of those rate constants, and that's going to give a bunch of numbers. We're also going to go 1 over those Kelvin temperatures. So 1 over 338 is a number. That's the first data point. 1 over 328 would be the second one, etc., etc. And then from from this, we can make a graph. So again, we're going to use Excel or Apple Numbers or Google Sheets, one of these kind of programs. And if you've done it correctly, you will get a nice straight line with a negative slope. So if you see the straight line with a negative slope, that's when we can apply linear regression. Once again, linear regression is going to be our good friends, as you can see. Now, from the linear regression equation, we should get a pretty nice value of little r, the correlation coefficient, which should be close to -1, minus 0.9, something like that. The slope of the linear regression is really important to us here. The slope equals negative EA over R. And again, E sub A is this desired energy of activation, or activation energy. The R value there is the 8.3145, the energy R we've used in previous problem sets. So negative 8.3145 times the slope will give us the energy of activation. And by the way, energy of activation is always a positive number. It's an energy barrier that has to be overcome to make reactants go to products. Now, the y-intercept also is important to us in this problem. Y-intercept equals natural log of A, and A is the frequency factor. And there's lots of interesting things you can do with a frequency factor in later courses. For right now, in Chem 222, we've already got enough things to think about. We're just going to calculate the value of the frequency factor. We won't do that much actually with it. So, in this problem, I would definitely use a program like Excel or Apple Numbers, turn T of K into 1 over T of K, turn K into natural log of K, on your y-axis, natural log of K, on your x-axis, 1 over the Kelvin temperature. And when I did this in my program, this is what I ended up with. The dots definitely formed a nice straight line. You can see it has a negative slope. It's quote-unquote increasing up and to the left. Anyway, I then did a linear regression on the data, and that's what this little part is right there. Y equals negative 12376x plus 31.273. My R value, negative 0.9999, so that's a really good R. Remember, as R is close to -1 with a negative slope, that means your data is definitely susceptible for linear regression analysis. Now, this is the graph that you need to make. This is the linear regression. Now we can use the slope to find E sub A, and we can use the y-intercept to find the frequency factor. So slope equals minus 12376, and that equals negative EA over R. Now R is 8.3145 joules per mole Kelvin. You can also use 8.3145 times 10 to the minus 3 kilojoules per mole Kelvin. It makes your answer automatically turn into kilojoules, which is cool. Anyway, if you do this to 3 sig figs, energy of activation 103 kilojoules per mole, 1.03 times 10 to the 5th. A, if you do that, A here, to figure that out, the y-intercept equals natural log of A. So to get rid of the natural log, you take the anti-natural log, this little e to the x. So A equals E raised to the power 31.273. That crazy frequency factor, 3.82 times 10 to the 13th. Frequency factors are always positive numbers, and they're usually pretty big numbers. And again, in future courses, you might be able to use that. But for right now, let's just report it and see good to go. But the energy of activation, super important. That's the value for this N2O5 decomposition reaction. Balancing nuclear reactions. And this process isn't too hard, but it is something that's really useful when it comes to studying the reactions that happen in the nucleus. And so you can see in all of these, there's either going to be some kind of piece missing, or it gives you some information and wants you to fill in the corresponding equation. These aren't too bad, at least not to me anyway. Here, let me write this out. So the first one is beryllium-9. It's reacting with something, and I'm just going to leave a blank right there. And on the other side, you have a lithium-6 and a helium-4. So you're trying to figure out what the missing piece is right there. And how you do this, like we talked about in lecture, is you just want to make sure the lower left numbers, the atomic numbers on the reactant side, equal the lower left atomic numbers on the right-hand side. So on the left-hand side right now, we've got a 4. We don't know what's inside the box, so let's call that x. So 4 plus x, and that equals the lower left numbers on the other side. So 4 plus x equals 3 plus 2. Well, you can probably see that 4 plus x equals 5. That means that x is going to be 1. So I'm going to put a 1 right there for that number. All right, you do the same thing for the upper left-hand numbers, the mass numbers. The mass numbers on the left will equal the mass numbers on the right. So 9 plus x equals 6 plus 4. You can see that in this case, it's also the upper number that's missing is also equal to 1. So in this problem, when you have a lower left-hand number of 1, you can look on the periodic table and just call it hydrogen, and that's totally fine. Sometimes in this chapter, instead of calling it just hydrogen, they'll call it a proton with the symbol P, and honestly, that's fine too. So any way you do this, you should see that a hydrogen is the missing piece. You can call it a hydrogen, which is fine. If you want to call it just a proton, put a symbol P right there, that's awesome too. So that's how you do these problems, not too magic about it. On B, same kind of thing, 95 plus 2, 97 equals 97 plus something. Well, if 97 equals 97 plus x, x is going to have to be 0. So the lower left-hand number on B is going to be a 0. On the other hand, 241 plus 4, 245, equals 243 plus x. On the second one there, B, you're going to have 2 and 0. Now, this one is a little bit strange compared to the first one. One of the particles you're going to see a lot in the nuclear chemistry section is a neutron, and a neutron gets 1, 0, n. But you can see here from the values in the upper left corner, you have like 2 pieces. So if you have a 2 up there and a 0 on the bottom, what you want to do is write it as 2, 1, 0, n. And that's like saying you have 2 neutrons, all right? That's the way to do this one. You don't put a 2, 0, n. You would write big 2, like as if we had 2 moles of something, but in this case, it would be saying you have 2 neutrons. So don't write 2, 0, n, write big 2, 1, 0, n. Cool for school. You can see that on the next one, it says there are 5 neutrons there on the product side. All right, so that's going to be helpful to you to figure out. So anyway, C, 92 on the bottom plus x equals 100 plus 0. There's 8 pieces missing, so the little lower left-hand number would be 8. And when you do the upper part, I'm pretty sure you have 238 plus x equals 249 plus 5, so 254. There's going to be 16. So on C, the missing particle is a oxygen 16. Now, sometimes in the past, I've had people write, instead of an oxygen 16, they'll write 4, 2 heliums, like 4 alpha particles, if you remember what it is. 4 times 4 is 16, 4 times 2 is 8, so mathematically it comes out to be the same as 116 oxygen 16. However, the oxygen 16 is definitely preferred, and here's kind of why. Let's say that I said to you, hey, let's go see a movie, and you were like, cool. So we'd coordinate our schedules, get to the movie, but then you say, hey, wait, can my brother go? And I'm like, yeah, sure, that's no problem. Oh, but your brother works at the time we were going to go, so we delay to a later showing. But then one of my friends says, hey, I want to go too, so we have to coordinate with his schedule. So why this is important, the more people you try and coordinate to see a movie, the harder it is to coordinate to actually see the movie, because one person works and one person has a birthday party, and et cetera, et cetera. So anyway, having two particles come together is a heck of a lot more likely and probable than having 4 alpha particles and a uranium-238 all happen to meet at the same time. So it's not very likely that you'd have 4 alpha particles for C. If you put that down, it's not the end of the world, because mathematically you've got it, and that's what I'm really pleased about. But usually smaller number of particles will be better than larger number of particles. Okay, the next ones all involve either a capture, a decay, or an emission, all right? They're all breaking down, but don't worry about that part. You focus on if they're being captured, if something is undergoing decay, or if you have an emission, all right? Those are really important. Electron capture means that an electron is going to be a reactant. The gallium-67 is going to break down once it captures the electron. So capture means reactant. So in the first one there, you would write gallium-67 plus an electron, 0 minus 1 E or 0 minus 1 beta is fine too. That's what you would write. And then to balance it, 31 minus 1 would be 30 on the right. 67 plus 0 would be 67 on the right. Gallium-67 decays to zinc-67 by electron capture. So that's how you figure it out. So again, capture means reactant. On the other hand, if you see that it's a positron decay or a positron emission, that means that that thing is going to be a product. So for E, a positron, which is the cool anti-electron, positron is going to be a product, and you're trying to find the missing piece. So the potassium-38 breaking down to X plus 0, so the top number is going to be 38. On the other hand, 19 is the atomic number for potassium. That breaks down to X plus 1, because positrons are plus 1. That has to be 18, and 18 is argon, so it's an argon-38 that potassium-38 is decomposing into. The last one, if you see something with a little m by the number, that means metastable, and that's a really high energy version of protons and neutrons, and they will decay into the normal form of the element plus a gamma ray. So for the last one there, you would write a little technetium with a 99M next to it, and that's going to break down to regular technetium without the M plus a gamma ray. That extra energy is released, and almost always it's a gamma ray, really high energy emissions. Calculate the binding energy in kilojoules per mole of nucleons for phosphorus in both the formation of phosphorus 31 and phosphorus 30. Now this is a really cool problem, and I'm going to break this question down to 3 different slides here a little bit. In the first question, we're going to look at the formation of phosphorus 30 and how to find the binding energy per mole of nucleons. In the second slide, we're going to look at the binding energy and how to calculate it for phosphorus 31 and the binding energy per mole of nucleons. And finally, we're going to compare the 2 answers and talk about what the answers actually mean. Now, in order to do these kind of problems, you must have some masses, and these numbers are all grams per mole. Here's the mass of a hydrogen atom, there's the mass of a neutron, there's the mass of a phosphorus 30, and the mass of a phosphorus 31. And on this first part here, we're going to focus on the phosphorus 30. If you're writing one of these equations out, you have the raw protons and neutrons as reactants and the atomic nucleus as the product. So because it's phosphorus 30, that means it's going to have 15 protons plus 15 neutrons. If you balance this nuclear reaction out, you'd have 30 on both sides, 15 on both sides, etc., etc. Anyway, this is like reactants going to products, okay? And this is what you do for phosphorus 30. So the first thing, like we did in lecture, is you want to find the change in mass. And you're going to find that the mass going in is actually greater than the mass that comes out. So remember that delta is always final minus initial. So that would be phosphorus 30 minus the 15 protons and 15 neutrons. So here's the mass of the phosphorus 30 given in the upper right corner. That's, you subtract from it the 15 protons and the 15 neutrons. And oh my gosh, you find a negative mass number. Now at first this is really weird because since balancing chemical reactions, you must make sure the atoms are the same sodium on both sides, stuff like that. What the heck, Russell? Okay. Well, what we're seeing here is actually the justification for why phosphorus 30 forms at all. Like if you think about with money, all right, people don't invest money unless they think they're going to make money. All right, that's kind of capitalism, I guess, there, but that's neither here nor there. In science, atoms don't form unless you're going to get some kind of energy out. There's a reason for them to form. And what Einstein did is you can take that change in energy and multiply it by the speed of light squared. Now, if you're going to make a mass into an energy, you have to turn the grams into kilograms. In SI units, a kilogram meters squared per second squared is equal to a joule. So you must turn my beloved and all chemists beloved grams per mole into a kilograms per mole. All right, so you can see there's an extra times 10 to the minus third that turns the grams into kilograms. But anyway, you multiply that by the speed of light squared, 2.998 times 10 to the 8th meters per second, and you get a very, very large number. And I turned it here into kilojoules, negative 2.419 times 10 to the 10th kilojoules per mole. This energy is being released once phosphorus 30 forms. And that is a huge amount of energy. Like if you think about acids and bases, all right, we calculated their change in energy at 10 to the third, maybe 10 to the sixth, maybe if we're lucky, kilojoules per mole. That's a lot of energy. But man, making phosphorus 30, you get some serious energy out, many orders of magnitude larger than the acids and bases and sodium reacting with metal kind of reactions. All right, there's a lot of energy, very, very exothermic. So this number right now shows you then how much energy is being given off. Technically, binding energy is the opposite of that energy. So it's really opposite the delta E value right there. So take the opposite of the negative, make it positive. A nucleon is just a proton or a neutron. So phosphorus 30 has 15 neutrons and 15 protons. Technically, then it has 30 nucleons. So the binding energy, the positive version, divided by 30 nucleons gives you this number, 8.064 times 10 to the 8th kilojoules per mole of nucleons. So for every nucleon formed, you're going to get that much mole of nucleons formed, you're going to get that much energy. Or that's the energy that the strong force has to provide, if you will, in order to make the nucleus stable, which is also kind of interesting. We're going to come back to this number in a little bit, so just bear with me here. What I'd like to do right now, though, is let's do the same process, but for phosphorus 31. Now, phosphorus 31 is very similar to phosphorus 30, except there are now 16 neutrons. Phosphorus 31 has one more neutron than phosphorus 30 does. But the process is going to be almost identical. We're going to find the change in mass. It comes out again to be a negative number. Mass has been lost, making phosphorus 31, but that's okay. We'll turn that change of mass into a changing energy, essentially. It comes out again to be a very, very big negative number. And we can calculate the energy, binding energy per mole of nucleons by taking the opposite of that number and dividing, in this case, by 31. So here's the binding energy per nucleon for phosphorus 31, 8.188 times 10 to the 8th kilojoules per mole of nucleons. And again, all these numbers are good because they justify why phosphorus 31 exists, all right? You get energy out. There's a reason for the protons and neutrons to come together to make phosphorus 31. That's kind of cool. But there's even more. In Chem 221, when we looked at isotopic abundance, we looked at the periodic table, and the value for phosphorus on the periodic table, let me grab mine here, the value for phosphorus, 30.974. And 30.974, if you round up, is much closer to 31 than it is 30. So we said, oh yeah, phosphorus 31 is more common. That's what we did in Chem 221. Now in Chem 222, Because the binding energy per mole of nucleons is larger in phosphorus 31 than it is for phosphorus 30, that means you get more energy out. You get more bang for your buck. If you invested money and you got 8.064 times 10 to the 8th dollars back, you'd be thrilled. That's a lot of money, by the way. Anyway, but if you could do the same investment and get 8.188 times 10 to the 8th dollars back, well, you'd get a whole 0.1 times 10 to the 8th more dollars. That's the one that you would invest with, right? You'd get more money back. Mother Nature does the same thing. She gets a lot of energy back making phosphorus 30. So that's why we do have a lot of phosphorus 30. But you get more energy back making phosphorus 31. So if you can get more energy back, you're going to make more phosphorus 31. So anyway, molar mass of phosphorus, there it is, even better sig figs than the one I had, is much closer to 31 phosphorus because you get more energy back making phosphorus 31 than you do phosphorus 30. So you can actually justify why some of the abundances are as they are, why there's more phosphorus 31 than phosphorus 30, why there's more helium 4 than helium 3, and the list goes on and on and on. Lots of examples of this. Okay, so that's it for problem set number 6. If you have questions on the material, I encourage you to check out the study guide and the concept guide for both chapter 17 and chapter 20. They're located both in the companion and on the website. There are also the online only chapter guides that might help as well for this particular section. You might also check out the reaction mechanisms guide. It's a handout that will help you further understand the intricacies of mechanisms when it comes to kinetics. Thank you for spending your time with me. I do appreciate it. Good luck with your studying. Have a wonderful day.